So continuing with logistic regression, we're going to explore further this idea of decision boundary. Now, previously we developed a probability model that, given the values of the features, our model found a probability. Now, remember, we did that in two stages. We have a linear function, but a linear function does not give a good probability, so we applied this logistic function to the linear function to get a probability value. And the interpretation was that this H was the probability that the classification of my item was equal to 1. And we mentioned that to make a decision, you have to make a threshold. So you can say that if the probability is more than 50% that the item has classification 1, then we classify it as 1. On the other hand, when the value of 8 is less than 0.5, we classify it as 0. Right? So the point really is that all you need to do is look at this value of theta transpose x. The logistic function is equal to 0.5 when the argument of the logistic function is 0. So I don't need to go through and evaluate g at all. All I need to do is say if theta transpose x is greater than 0, I classify as 1. When theta transpose x is less than 0, I classify as 0. Right? So I evaluate this theta transpose x. Here it's called z. And when z is greater than 0, I classify as 1. When z is less than 0, I classify as 0. So from this point, the g is not really important. We only focus on this expression here, theta transpose x, and the sign, whether it's, and the value, whether it is positive or negative. All right, so just go through that. Now, in the case of one variable, that just means we evaluate a number. In the case of two variables or two features, it becomes more interesting. Suppose, for example, we're trying to determine credit risk, and we have two variables that we're looking at. And here we have previous data and their classifications. And suppose we have obtained our model with these values of theta. Now, our determination is going to be based on theta transpose x is greater than or less than 0. So geometrically, what does that mean? If theta transpose x is greater than or less than 0. Well, theta transpose x is a linear function. And if you want to know when this is greater than or less than or equal to 0, you can solve this as equal to 0. That's going to be a line. Greater than 0 means that you're above the line. Less than 0 means that you're below the line. Okay, right? So here, above the line means x1 plus x2 is greater than or equal to 5. Below the line means x1 plus x2 is less than 5. The decision boundary is when x1 plus x2 is equal to 5, right? When this expression is equal to 0, right? So our mathematical specification of the decision problem has led to a very intuitive and clear geometrical representation. You can simply plot all of your data in some space, and the decision criterion will determine the boundary, On one side of the boundary, you make one decision. On the other side, you make another decision. Now, here I want to reemphasize that in this case, you can find a boundary that makes perfect decisions on the data that you already have. In the general case, you cannot find a boundary that perfectly separates the data you already have. And we'll see examples of that as we go along. Now, the PowerPoint slides give several other examples that I want to skip. But let's go on to elaborate the method. Remember, in linear regression, we added nonlinear features, which could improve the fit. Now, in logistic regression, we can also add nonlinear features. So far, our separating boundary is a line, but if you add nonlinear features, you can have a separating boundary that's a curve. And the nice thing is that to fit these nonlinear features, the procedure is very much the same as in linear regression when we had models with nonlinear features. Right? So the goal is different, but the mathematical techniques are similar. So let's see an example of a nonlinear decision boundary. Suppose we have two classes of data that are arranged this way. Now, obviously, there's no line that can separate these two, but they could be separated by a circle. Now, a circle is simply a nonlinear function. So if we can create a decision boundary that corresponds to this circle, then we can develop a good classification scheme. And we can do that. If we have a probability model that depends on this quadratic function, I can find coefficients theta 0, theta 1 up to theta 4 such that this function, theta 0 x 0 plus dot 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 plus theta 4 x2 squared equals 0 corresponds to this circle. And in this case, when this function is bigger than 0, that will correspond to a point outside. Less than 0 corresponds to a point inside. Now please remember that x0 is equal to 1. So we really only have two features here, x1 and x2. Okay, so for instance, assume that we've obtained these values of theta. Then we have this function, theta transpose x equals minus 4 plus x1 squared plus x2 squared. Now if you set this equal to 0, that's the same as x1 squared plus x2 squared equals 4, which is exactly this circle. So this gives us a decision boundary. And you can verify that if you take a point outside of the circle and evaluate this function here, you'll get a number bigger than 0. And if you evaluate a point inside, you get a number less than 0. So just the same as before, only now we have a nonlinear boundary instead of a linear one. In summary, we predict y equals 1 when the value is bigger than 0. Predict y equals 0 when the value is less than 0. Okay, so very clear, complete picture. Once again, emphasizing the relationship between linear regression and logistic regression. The nonlinearities in linear regression were able to make you develop a fitting function that has a more complicated shape. The nonlinearities in logistic regression enable you to form a more complicated decision boundary. Okay, this video has been fairly short, but I think we'll stop here, and next time we'll move on to finding the cost function. Remember, we have to have some kind of cost function to evaluate and compare different models. So see you next time.